The Burj Dubai is so tall that in the highest floors you are even above the clouds. Today at ScienceWorks, we will hear directly from a structural engineer who worked on the Burj Dubai. My name is Brett. I am a manager of guest programs here at the Museum of Science and Industry, and I have the privilege to introduce Mr. Lawrence Novak at ScienceWorks today. Mr. Novak is the Director of Engineered Buildings for the Portland Cement Association, and he has 20 years of experience as a design structural engineer on high-rise, mid-rise, and special-use structures around Chicago and throughout the world. Mr. Novak earned a Master's of Science in Structural Engineering from the University of Illinois. As an associate partner with Skidmore, Owings & Merrill, LLP, he was the senior project engineer responsible for the structural design of the Burj Dubai. He also worked on the 92-story Trump International Hotel and Tower in Chicago and the renovated Guggenheim Museum in Spain. Mr. Lawrence will speak to us today about building it high.
Thank you very much, Brett. I want to thank you all for coming here today. We've heard several speakers. The previous speaker talked about what was deep down under the sea. Well, I'm going to take you to the top of the world. I've got the funnest job in the world. I get to design buildings. But you know, building is really human nature. I love this slide. That's a picture of my daughter. Of course, she's now 15, so she hates this slide. But really, what do we do when we're young kids? We want a set of blocks, whether it be Legos, wood blocks, whatever. And what's the first thing we do with them? We see how high we can stack them. I got the greatest job in the world. I just get to play with really big blocks. You know, we all know which way is up. It's something we learn as basic as children. Engineering, architecture is really all about what we're learning through our whole lives. We all know you put the pyramids with the flat side down and not the point down. This is very different than robotics or electrical engineering or something like that where you don't understand it until you put your finger in a socket. This is something inherent to the human condition. So what kind of building materials do we have? I apologize. I'm going to move around a little more than the previous speakers. I got the advantage, I'm a local boy, so I got to bring all my toys in. You know, the first building materials were bricks. Bricks are dried clay. You dig them out of the ground and you dry it and you make the bricks. I love the pyramids. They were the tallest building for the longest time. And they were built for one occupant. He was dead. No windows, no bathrooms. You know, bricks are interesting materials. You want to see? That's a foam brick. The tallest brick building in the world is the Monadnock building here downtown Chicago. Why do we not build any taller buildings than this in brick? Well, this building, the base of the building, the bricks are 6 feet thick to hold up the load of all the building above. So we quickly needed another building material available to us. We use concrete a lot. Concrete is cement mixed with rocks to form concrete. It's a very strong man-made material, and it's flowable. You can take any shape you want. We also have structural steel, which is mined from the ground as an ore. Starting to see a trend. To build the world's tallest building, we have to dig a hole. We get our materials from Mother Earth. It's very sustainable. It's very recyclable. All of our materials are recyclable, including concrete. Also, a very interesting material is cables. Very, very strong, but very flexible. No, I'm not Superman. It's extremely strong material, but very flexible. And using these basic building materials, we can do all these exciting projects. Fabulous architecture. Let's talk a little bit about materials. My assistant today is Alexander Novak. He's going to do a little concrete testing for us. What we have here is a piece of concrete. Unreinforced means it's got no other materials in it except concrete. And concrete by itself is somewhat brittle. But let's see if we can break it. Those are pieces of steel and lead. Cool. But did we have any warning that it was going to break? No. It didn't even deflect much. It just broke with one solid crack. So what do we do differently? We want ductility. So what we do is we mix the two materials together, concrete and steel. We make a composite of the two. So I'm taking the same beam, but I've added nothing more than a small wire of steel. Everyone can see that? And what we do is the concrete's very good in the compression, the top part of the beam. But in the bottom part of the beam where that crack opened up, the steel takes that load. It's a very small amount, but it makes a great combined material. Can you pick up the middle piece? Okay. Of course, the trick with any type of experiment, you never know what's going to happen. That's the cool thing about being a scientist and engineer. You learn from doing. Now, that's about where the first one broke, if I recall. Now, even though these pieces are smaller, these are lead, so it actually is heavy. I've made no difference except adding a small wire, like a piano wire, to this material. It's actually already cracked because it broke at the same point at that other one, but that steel bridged the cap and is keeping it together. We'll probably be able to get them all on, actually, Alex. Amazing. We can even add my weight. Amazing how we can make two materials that are very, very different, but combine them to make the ultimate strength. And a lot of the buildings we recognize. This is which building? Hancock. Oh, I love this audience. Great group. You know, what's this over in this corner? What's this? This big circle. Illinois Quarter. Anyone ever look very closely at their Illinois Quarter? The Hancock's outlined in the back. Tall buildings tend to be an icon for what we do. It really tends to represent the people and the culture around it. Very interesting thing about the Hancock building is it's got the X's going up the side, right? It literally wears its structural system on its sleeve. Everyone can tell what holds this building up. I actually even understand the units with the X braces through it demand more money because it's such an icon to the city. But when you look at these, I don't want you to think of them as X's. I want you to think of them as triangles. Here I've got a nice kid's toy, made up into a pyramid. Would you be willing to help me, little young lady? What's your name? Come on up, Emily. What you to do is push down with your finger and see if you can crush that. Was it easy or was it hard?
Medium.
Medium? Most people think hard. She must be strong. So we've got this pyramid. What I'm going to do is remove one leg of that pyramid, but not even a vertical leg, a piece of the horizontal. So I still have a pyramid, right? Stand to the side and see if you can crush that so people can see. Easy or hard? Easy. She says it was easy. The key is completing the triangles. So if you actually look at Hancock, you'll see those triangles complete around all four sides of the building. Thank you very much, Emily. You can sit down. A lot of times, so triangles are very, very useful shapes for structural engineers in building architecture. You see them a lot on highway bridges even. You'll see them. What's another shape that we tend to see? Well, let's still stick with triangles a little bit. This is a triangle, right? What's this? Shark's tooth. Not just a shark's tooth, though. This is a Megalodon shark tooth. Prehistoric shark. They used to eat whales. They could swallow me and my son Alex whole. But this triangle survived through the millennia to be able to, because of its strong shape, and it's very useful for cutting. What's another shape that we use that are curved? Arches. Yeah, arches. So what's this arch a shape of?